Hi, this is a small lecture on the topic software product metrics. So, the agenda for the lecture is as follows: software quality, a framework for product metrics, a product metrics taxonomy, metrics for the analysis model, metrics for the design model, and lastly, metrics for maintenance. So, if you see the concept of examples of metrics from everyday life, so we have a lot of metrics, right from working and living, where you have cost of utilities for the month, cost of groceries for the month, and so on. If you are a college student, grades received in the class last semester, number of classes taken each semester, and so on. And if you love to travel, then time to drive from home to the airport, amount of miles traveled today, cost of meals and lodging for extra day, and so on. So these are some of the examples of metrics from everyday life. Why have software product metrics? So software product metrics would obviously help the software engineers to better understand the attributes of models and assess the quality of the software. It also helps software engineers to gain insight into the design and construction of the software. So, if you talk of software product metrics provide a systematic way to assess the quality based on a set of clearly defined rules. So, these kind of metrics provide on the spot rather than after the fact insight into the software development. And this shows why software product metrics are important. Coming to software quality, we have already known in software engineering that software quality is the bedrock of software engineering. So, if you look into the definition of software quality, the definition clearly says conformance to explicitly stated functional and performance requirements, explicitly documented development standards, and implicit characteristics that are expected of all professionally developed software. If you look into this definition, which probably runs to about 3 lines, there are 3 important points that you can probably look at from this definition. The first is explicit software requirements, which are obviously the foundation from which quality is measured. So, lack of conformance to requirements is obviously lack of quality. The second one is specific standards. So, if you look at specific standards, they define a set of development criteria that guide the manner in which the software is engineered. So, obviously, if the criteria is not followed, then lack of quality will result. The third one says implicit requirements. Implicit requirements mean they go unmentioned. So, if the software conforms to its explicit requirements but fails to meet the implicit requirements, then obviously the software quality is going to be at suspect. So, if you look at the properties of software quality factors, so there are certain factors that could be directly measured, and there are certain factors that could be measured only indirectly. So, software quality factors basically focus on 3 important aspects. You start with product operation, then move on into revision, and then to transition. So, ISO is the International Standards Organization. The software quality is defined by ISO 9126. The ISO standard, most of you might know, basically standardizes the process, and ISO does not certify the product. So the software quality factors of the ISO 9126 are functionality, reliability, usability, efficiency, maintainability, and portability. If you look at functionality, functionality says the degree to which the software satisfies the stated needs. Reliability says the amount of time that the software is available for use. Usability says the degree to which the software is easy to use. Efficiency is the degree to which the software makes optimal use of the system resources. Maintainability means ease with which enhancement can be done, and portability is very obvious, where how easy it will be for me to port this software from one platform into another. So software quality also could be measured by what is called the SEI CMM. CMM stands for Capability Maturity Model. Capability Maturity Model defines 5 levels, level 1 through 5. 1 being initial, 2 is repeatable, 3 is defined, 4 is managed, and 5 is optimized. Each of these 5 levels defines certain key process areas. The highest level being level 5, which is optimized, and the key focus of this level is continuous process improvement. And our key process area is basically defect prevention, then process change management, and technology change management. Now moving on into the framework for product metrics. So we have something called measure, measurement, metric, and indicator. So most of these terms are used interchangeably, but they have very small subtle differences. Measure provides a quantitative indication of the extent, amount, dimension, capacity, or size of a product or a person. Measurement is the act of determining a measure. Metric is a quantitative measure of the degree to which a system, component, or a process possesses a given attribute. An indicator basically is a metric or a combination of metrics that provides insight into the process, project, or the product. So what is the purpose of the product metrics? These obviously aid in the evaluation of the analysis and design models. They facilitate design of more effective techniques, and they also provide stability. So when you look at the activities of a measurement process, it starts with formulation to collection to analysis, interpretation, and feedback. Formulation basically involves formulating the problem. Collection basically involves collecting or accumulating data. Analysis basically involves computation of the metrics, and analysis obviously requires application of certain mathematical tools. Interpretation is after the metrics are computed, what is the insight that you derive from the computed ones is what is called interpretation, and the last one is feedback. Feedback basically is nothing but recommendations derived from the interpretation of the metrics. So characterizing and validating metrics. So there are certain key things that you always need to remember. For example, a metric should have certain desirable mathematical properties, where probably the range could be somewhere between 0 to 10. It cannot be 0 to infinity or negative. It should be on a rational scale rather than an ordinal scale, and so on. So each metric should definitely be validated empirically, and if a metric represents a characteristics that increases when positive traits occur and decreases when undesirable traits are encountered, the value of the metric should also be increasing and decreasing, and so on. So to put in simple terms, they are all directly proportional. So if you look at collection and analysis guidelines, it is always important to note, whenever possible, all of these data collection and analysis should be automated in order to minimize errors. So we have goal-oriented software measurement, where you have the goal, question, metric paradigm, where it emphasizes on the goal, a set of questions, and a well-formulated metrics. So if you look at example questions, is the complexity of each component within the bounds that will facilitate modification and extension, is one example question for this goal definition. So attributes of effective software metrics. Whenever I say my metric is good, what are the attributes it should probably possess? So it should be simple and computable. It should be empirically and intuitively persuasive. It should be consistent and objective in nature. It should be consistent in the use of units and dimensions. It should be programming language independent, and this should serve as an effective mechanism for high quality feedback. So we move on into what is called the product metrics taxonomy. So we have metrics for the analysis model, the design model, coding, testing, and maintenance. So when you look at metrics for the analysis model, we have something based on functionality delivered, system size, and specification quality. When you look at metrics for the design model, we have architectural metrics, component level metrics, interface design metrics, and specialized OOD metrics. If you look at metrics for the source code, we have complexity metrics that measures the logical complexity of the code, and length metrics provide an indication of the size of the software. Then we have metrics for testing like the branch coverage metrics, defect related metrics, testing effectiveness metrics, and in-process metrics, and so on. And we move on into the metrics for the analysis model. We would be probably trying to discuss this metric for the analysis model called the function point metric in a bit detail. If you look at the concept of a function point metric introduced in 1979, where there are hundreds of books and papers written on these function points. So this basically uses the historical data. Function point will be used to estimate the cost, predict the number of errors, and forecast the number of components. So if you look at the key concept of a function point metric, we have something called the IDV, the information domain value, based on the number of external inputs, the number of external outputs, the number of external inquiries, the number of internal logical files, and the number of external interface files. There are 5 IDVs that play a key role in the function point metric. So this is how it looks like diagrammatically. So when you go for the function point computation, you identify and collect the IDVs, you complete the table as shown below, and then you try to associate a weighting factor based on the complexity value. Then you evaluate and sum up the adjustment factors. There are 14 such adjustment factors, and you try to probably associate a value between 0 to 5 for each of these adjustment factors and then sum them up. And then you compute the number of function points. The function points is computed using the simple formula function point equal to count total into 0.65 is a constant plus 0.01 is again a constant multiplied by sum of Fi. Fi basically stands for the adjustment factor. These are the 14 different value adjustment factors. And for example, is the performance critical? Does the system require online data entry? Is the code designed to be reusable? Is the internal processing complex, and so on and so forth? And you associate a particular value to each of these. After you do all of these things, then you go for computing the function point by substituting in this formula, and you get a value of somewhere around 56. So what does that value indicate? That value indicates certain things based on historical data. I could say probably one function point translates into 60 lines of object-oriented code. 12 function points are produced for each person month of effort. An average of 3 errors per FP are found during analysis and design. An average of 4 errors per FP are found during unit and integration testing. And what is the use of this numerical value? It obviously is helpful for project managers to revise their earlier estimates. So then going on into the metrics for the design model, we have the architectural design metrics. And they are black box because they do not require any knowledge of the inner workings of the software component. Then we have the hierarchical architecture metrics based on structural complexity, data complexity, and system complexity. So structural complexity has a very unique formula. S of I is equal to F out of I square. F out is called fan out, where it basically indicates the number of modules immediately subordinate to a module I. Data complexity D of I is equal to V of I by F out of I plus 1, and the system complexity is computed very easily, which is the sum of the structural complexity and data complexity. So it very clearly says as each of these complexity value increases, the overall architectural complexity also increases. Obviously, if this increases, then obviously you need to put more effort into integration and testing, and that will also increase. You also have something called the shape complexity, where size equals n plus a, where n denotes the number of nodes and a denotes the number of arcs. You can also compute what is called the connectivity density, otherwise called the arc to node ratio. The formula is going to be simple: arc to node ratio, so R equals a by n. And this connectivity density provides a simple indication of the coupling in the architecture. So coupling basically talks of the interdependency between modules, and that is how you can probably conclude if coupling is more, it is not good, right? So we always require low coupling and maybe higher cohesion. Then we have metrics for the object-oriented design, like the size, the coupling, cohesion. So lower coupling, higher cohesion. Primitiveness means atomic, beyond which you cannot break it further. You also have specific class-oriented metrics like the weighted methods per class, depth of the inheritance tree, and so on. And all of these are basically based on the number of children. So you also have coupling between object classes, response, and lack of cohesion in methods. You also have the metrics for maintenance. So the metrics for maintenance is basically based on what is called the SMI, the Software Maturity Index. And this SMI provides an indication of the stability of a software based on changes that occur for each release. So the formula is simple: SMI equals MT minus FA plus FC plus FD divided by MT. MT stands for modules in the current release. FA stands for modules in the current release added. FC stands for modules in the current release changed. And D stands for modules from the preceding release that were deleted in the current release. So what do you get? You get a numerical value again, or a fractional value also sometimes, 0.5, 0.6, or at the max 1. When you will get maximum 1, when FA plus FC plus FD is 0, then you get MT is X divided by, again, MT is X, you will get a value 1. So what is the conclusion? As the SMI, the Software Maturity Index, approaches 1, we can conclude that the software product begins to stabilize. So the average time to produce a release for a software product can be correlated with this SMI, and that is how the SMI is a Software Maturity Index, which is a suitable metrics for maintenance. So these are the software product metrics, and this is what you have learned in this lecture.